Good morning, students. Today we will continue our chapter 9 Mechanical Properties of Solids, and our today's topics are elastic potential energy of a stressed wire, Poisson's ratio, elastic after effect, elastic fatigue, and elastic hysteresis. So let us begin with our first topic. So students, our first topic is elastic potential energy of a stressed wire. So let us define what is elastic potential energy. So students, when a wire is stressed, the interatomic forces comes into play, which opposes the change. So the work has to be done against this restoring force. So the work done in stretching the wire is actually stored in it as its elastic potential energy. Okay. So students, let us begin with the expression for elastic potential energy. Okay. So students, suppose a force F is applied on a wire of length L and it increases its length by delta L. Okay, a small change in length. Initially the restoring force in the wire is 0. Okay, so the restoring force was initially is 0, and when the length is increased by delta L, the internal restoring force from 0 will become as F, that is the applied force. So students, let us take the average internal force for an increase in the length delta L of the wire. So initially the force on the wire was 0, you can see, and when there was a change in length, that was force F. So let us take the average internal force here, that is 0 plus F upon 2, that will be giving F upon 2. So let us calculate the work done on the wire. So students, you already know the formula for work done. What is that? Work done is equals to force into displacement. So here, just putting the values, work done W is equals to average force into increase in length. Okay. So simply putting up the values here, W is equals to F upon 2, average force, and delta L is the increase in length. So students, this work done is stored as elastic potential energy U in the wire. Okay. So students, simply U is equals to half into F into delta L, that is U is equals to half into stretching force F into delta L, that is increase in length. So students, let A be the area of cross section of the wire, then U is equals to half into F upon A into delta L upon L into A into L. What is this now? Students, simply to get the desired expression, we have to multiply the numerator and denominator by AL. So you can see here in the numerator AL upon in the denominator also AL. We have multiplied it. So students, let us see here in the second expression, U is equals to half. This F upon A becomes stress. You already know that force upon area is equals to stress. Delta L upon L, you know, change in dimension upon original dimension, that is strain, and area into length is equals to volume. So we will write the volume of wire here. So this expression gives you the elastic potential energy, and if you will write this as elastic potential energy per unit volume, means this volume I'll send here. Okay, or if you will write elastic energy density, that is elastic potential energy per unit volume, so it is represented by small u is equals to elastic potential energy upon volume. So your expression becomes here small u, that is elastic energy density is equals to half stress into strain. Okay, you know students, stress is equals to Young's modulus into strain. This is actually the formula. Young's modulus is equals to stress upon strain. So we can write here stress is equals to Young's modulus into strain, and just putting this in the above equation, we get U is equals to half into Young's modulus into strain, that becomes strain square. And units of this is elastic potential energy is in joules, and for elastic potential energy per unit volume, or we can say that elastic energy density is represented by joules per meter cube. Okay students, let us move to the next topic. So our next topic is Poisson's ratio. It is very easy topic students, so let us see what is that. So in Poisson's ratio, when a wire is loaded, its length increases, but what happens beta? The diameter decreases. So let us see, the strain produced in the direction of applied force is called longitudinal strain, and the strain produced in the perpendicular direction is called as lateral strain. I'll explain it further. So students, within the elastic limit, the ratio of lateral strain to the longitudinal strain is called as Poisson's ratio. So longitudinal strain. So longitudinal strain, you already know, it is the change in length upon original length. And what is lateral strain? It is actually the change in the diameter. So the change in diameter is represented by delta D, and this minus sign is representing the decrease in the diameter of the wire. So lateral strain is represented by minus delta D upon D. Okay students, and Poisson's ratio is the ratio of lateral strain upon longitudinal strain. Simply putting the above values, we get Poisson's ratio is equal to minus delta D into L upon D into delta L. Okay, so here minus sign shows that the length increases, the diameter of the wire decreases. And students, Poisson's ratio is actually the ratios of two similar quantities, so it has no unit. Okay, let us move to the next topic. So our next topic is elastic after effect. So what is this elastic after effect beta? So the delay in regaining the original state by a body on removal of deforming force is called as elastic after effect. For example, if I am applying some force on a body, okay, and that body delays after the removal of deforming force, the body takes some time to regain its original position or original shape. I would say original shape. Okay, so this is called as elastic after effect. Okay student, so here I have taken an example. In the internal mechanism of a galvanometer, quartz or phosphor bronze are used because their elastic after effect is very small. Whereas, for example, if I take a glass fiber, it takes hours to regain its original state. Okay students, let us move to our next topic. So our next topic is about elastic fatigue. So let us understand what is it. So students, elastic fatigue is defined as loss in the strength of a material. Please note this, it is the loss in the strength of a material caused due to repeated alternating strains to which the material is subjected. So I'll make you understand further here with an example. So just take a hard wire which can be broken by bending it repeatedly in opposite directions as it loses its strength due to the elastic fatigue. Students, I will take one more example here, that when a material is subjected to continuous strain, okay, within the limit, but if the strain is continuous cyclic, okay, so at a time, after some time, the material will lose its strength and it will fail. For example, I'll take an example of railway tracks. You know that the railway tracks laid down is not for whole life. It keeps on changing. Okay. So why? Because continuously they have to bear the weight of the trains, okay, moving on them. So continuously the railway tracks are used by the trains, okay, and continuously they have to bear the strains, so they get failed after some time and some accident can cause. So to avoid that, they are being replaced. Okay, so this was elastic fatigue. Let us move to the next topic. So our next topic is elastic hysteresis. Let us see what is elastic hysteresis. So students, you can see there is a below figure that shows a stress strain curve for a rubber sample, which is when loaded and then unloaded. Okay, and you can see here for increasing load the stress strain curve is OAB. This is the OAB curve which is showing when it is loaded, when the rubber sample is loaded. This curve represented here shows the loading, and for decreasing load the curve BCO represents the decrease in the load. So you can see here the second curve here. This shows the decrease in the load. Okay, so students, the fact that the stress strain curve is not retraced on reversing the strain is known as elastic hysteresis. You can see here this curve OAB is not retraced. It is not retraced with the same path. It has taken another curve here. You can see BCO. Okay, so students, the area under the curve OAB represents the work done per unit volume in stretching the rubber. Okay, and the area under the BCO represents the energy given up by the rubber on unloading. Okay, so this shaded portion, actually this shaded portion, the area of this shaded portion of this hysteresis loop represents the energy lost during the loading and unloading cycle. So students, I give you a small task that just you have to study about some application of elastic hysteresis to get more idea about it, so that this topic would be more clear. Okay, so our topic ends here. For any doubts, you can contact me on my personal WhatsApp. Thank you students. Have a nice day.